Thorsten Ludwig. He's a master's in physics. He is working as a research assistant at the Technical University of Berlin. He's president of the German Space Energy Association, another year here. He's been doing research into medium energy collisions, quantum objects, plasma, and spectroscopy. He founded a charitable organization called Binotech. It's to encourage energy research. He's probing zero-point energy and electrogravitics besides. He has his doctorate now. That's new this year. He just got his doctorate of natural science in February in atomic physics. And he's going to be telling us a lot about the new developments in European energy research. Thorsten Ludwig.
So, yeah, welcome. Nice to be here again. I will tell you, huh? Mike? So, is it better now?
Hold on. Try it again.
Yeah? Okay, now you hear me? Yeah. Good. So, welcome. Nice to meet everyone. I think very nice conference so far, and feel privileged to speak to you again, this time about a different topic than last year. So the topic is zero-point energy, and let's see if this works. Do we have to turn this on? John?
I think the reflection is... when you're ready, we'll put it back up there. Is it page up, page down working?
Yeah? Well,
Try it.
no?
Now I'll try it. Oh, you're pushing the other button. Let's see. Now. There you go.
Great. Okay. So, small introduction to the zero-point energy. I think quite a few of you might have been here last year. So you heard the feasibility study from Tom Malone, and he has presented yesterday as well. So, as well as Maury B. King, who presented yesterday on zero-point energy. So this, I will not start from zero and give you some little bit of a different some news, some new experiments, some latest developments in the field to update you about it and mention some more aspects that I haven't heard here about the topic. So basically what you should know already is that space is full of energy and that we can actually use that, by theory at least. So the content of my talk will be as such. First, we have the small introduction. Then we go into some fundamentals to update everyone. Some of you might not have heard anything about the topic yet. So a little bit about the history, some basic concepts and experiments. Then the current research. And then I've brought a practical example of a free energy machine, which is being sold over 36,000 times with a guarantee that it works. So I will present that here with some animation and some little movie, and I've brought the thing here so everyone can look at it. So when I was thinking about which way to go, I thought, should I bring more complicated formulas or more beautiful pictures? So I decided to go the way with the more beautiful pictures because I think formulas are not that interesting, you know. All these formulas are related to the Carcinoma Effect, by the way. But if you really jump into this quantum field theory, then things become quite difficult. So we won't do that. So the history is quite interesting. I'm coming from Berlin, you know, so 105 years ago, Planck announced in a small audience like this, he talked about, for the first time ever, about the quantization of energy. And so up to the 1920s, quite a lot of this research actually was done in Berlin. So Planck, so 1900, for the first time, he had that formula up there. Let's see if we have some pointer here. So this was the first quantization of energy. And then here in 1912, for several reasons, he came up with this plus 1.5, which is like the first time the zero-point energy came into the game. And it's quite interesting how Planck, and especially Nernst, in 1916, he was the first one. I think there's an N missing here. He was the first one who really went into this idea of zero-point energy. And by that time, quantum mechanics was really not developed at all. The quantization of energy was there, and Nernst, he was only doing statistical physics, so no atomic physics or things like that. That came with Bohr, the Danish physicist. In the 1920s, he developed his atomic model, and Heisenberg, they went more deeply into this concept of the zero-point energy as we know it today, and then Schwinger and others in the 1950s, they developed this quantum field theory, the relativistic quantum mechanics, and so forth, and slowly developed the picture as it's been presented usually here. So, but already in here, Einstein and Stern and Nernst, all in Berlin around the 1910, 1916, they talked about these things, and only with statistical arguments, they already came to the conclusion that there had to be this zero-point energy. And basically, if they looked at the thermal radiation, it was in the high energy region that there were some difficulties if you would not use this 1.5. So that's just basically for the record. So in this history here in 1917, and then Casimir in 1948, they kind of laid the grounds. They laid the grounds for what we know about zero-point energy today and how we look at it. And so another very important thing is this uncertainty principle laid out by Heisenberg, where he got also the Nobel Prize in 1924. So for us, this uncertainty of time and energy is quite important because it kind of smears this energy and time. So if we look at things, it's like a credit law of the universe. You know, you can take that much energy for that much amount of time. It just has to be less than h-half. So in that sense, this is quite important because by that, these virtual particles, so fluctuations, these photons, electrical fluctuations, and particle coming into being and going out of being as the zero-point energy is usually described, all that comes basically from this uncertainty principle. And where does the uncertainty principle basically come from? It's also this particle-wave duality, because if you look at a particle, you can say, well, it is at a certain point at a certain time. But if you look at a wave, a perfect wave is spread out into infinity. So then you start to realize why this is happening. So, and this leads to the basic concept of zero-point energy. So here's some more graphics that I haven't made. I've taken from some books, so whoever has made them, please take the credit for it. It shows here, like if you have, this is called the quantum mechanical system, a harmonic oscillator. Why do we take a harmonic oscillator? It's like this. If you have any stable point in any system, if you apply simple mathematics to it, you always end up with a harmonic oscillator if it's a stable point, because small derivations from this point you can always describe as a classical harmonic oscillator or as a quantum mechanical harmonic oscillator, but then you have here, it never stands still. There's always some energy which is like the ground state and that has this 0-point energy. So here also, if you have a cavity, if you have a chunk of space, so to speak, then you have these modes in there, these possible electrical electrical energy formations in the space, and also these, they can never be zero. There always is this small 0-point energy. All these are very simple systems. So if we then go to real space, 3D, it becomes a lot more complicated if you do the theory right, which we will not do. So this is just to get some feeling for it. So the next important question is how much energy contains like a chunk of space. And these are the basic formulas for that. And notice here the omega to the third power, cubic power. So that's why you have here is as if the frequency goes up, you have a lot more energy. So then this obviously will become infinite if you go to infinite frequencies. So one of the usual arguments is that like at around wavelengths of the Planck length, which is quite small, 10 to the power minus 43 meters around that, that you kind of stop your integral there. But that's debatable, definitely. So we will go a little bit into that later. But right now, we just notice that that the high frequencies contribute a lot more to the 0-point energy than the low ones. And if you then kind of apply some termination of your integral, then you come up with this 10 to the power 93 grams per cubic centimeters as the energy density, which Tom Valone mentioned yesterday. So here are some of the artist's kind of viewpoints. Here you see this animation of some background noise, as it was called, or, well, I'm reluctant to say it's background noise, because if it's 10 to the power 93 grams per cubic centimeters, it's so much more than anything else that is contained in that space that we shouldn't call it background. It's a foreground energy, and the background is a normal mass. If that picture is correct, which, like I said, is debatable, how much energy is really contained, we will see. Because I will tell you later, this is another animation which kind of shows if you look very closely into space, you get this field, these electrical fields. It becomes like chaotic stochastic events. So all these are pictures of the 0-point energy. Oops. Well, there I am. John? Well, he's gone. Huh? Use the laptop, yeah, good idea. So, sorry about that, but I have to go back. He said that's the one for going back, so I guess. I have to get there somehow. Sorry. Okay. So here are some of the main experiments that have been done. I'm an experimentalist myself, so I think experiments are always a good way to determine if a theory is worth something. So actually the first one who was Lamb, who measured in 1947, he measured the spectrum of hydrogen very exactly with some new methods that came out of the Second World War. And there were a lot of scientists now free to do something else. So it was a very good time. So there was Lamb. And the only way to explain that shift was by calculating the influence of this 0-point energy of this background field of space, and it shifts the energy levels of hydrogen just a little bit. But there was very much went together with a theory developed by Schwinger and others at that time. So it was like the first thing that made 0-point energy important. The first experiment was where it was actually seen Then came Casimir in 1947, 1948, with his suggestion of his famous effect, but it wasn't only until later that it was really measured. So at that time, it was not so important. Then you have the measurement of the electron charge. The electron develops kind of a cloud around itself of electrons and positrons called vacuum polarization, and that has been measured in detail, and it's also quite, it goes together with its fine structure constant, which also changes. This has been done in the big accelerators in the 80s, and it's all that, the quantum field theory and the zero-point energy is very much in accordance with the quantum field theory. Then you also have the liquid helium. That helium is still liquid at very close to 0 Kelvin. Also that it comes from this zero-point energy that the atoms, the helium atoms, they move too much. So at 0 temperature and certain pressures, it will not become solid. It still stays liquid. And then there are some magnetic systems that you can study with neutrons and stuff, and they show huge zero-point energies because you can kind of set the system in such a way that the zero-point energy of the magnetic system is quite large compared to other energies. So you see even at 100 degrees Kelvin, you see very large amounts of zero-point energy there. So this is just to back up what we said. I like to emphasize something that hasn't been mentioned here that strongly before, but for the people who do this sort of physics, the high power accelerators, for them, how do I go back? I don't know, because this one doesn't go back.
Okay, try it again. Okay, oh, I see what happened. Okay, push the button on below it once. Okay, now try going back. There you are, sir.
Okay. So, sorry for that. So here we see the 4 basic interactions, and these are Feynman graphs which kind of show these elementary interactions. And this is, for example, sorry it's in German, I couldn't translate it that fast, it's a picture. And here you have the photon, which kind of carries the electromagnetic force. Well, this picture is like a standard textbook picture of the interactions. I just want to show you how integrated the zero-point energy is into the modern viewpoints of physics. It's not somewhere aside, it's very much in the heart of it. And even though not everyone in the field of like applied physics will use these pictures because they are doing something like more like electronics or engineers, but for the people who work in the accelerators, for them, if they want to calculate any of these reactions that you see in the next picture, they fully have to apply these methods to get to their conclusions and measurements. And so you have, these are the virtual photons which the vacuum consists of, you know. If you have any boson or particle which has a start and the end in a picture like this, then it's called a virtual particle. So you have the photon here, you have a gluon here for the strong force, and you have a W boson here for the weak force, and the pion here for another picture of the strong force if you look at the proton and neutron and not at the quarks. So for this sort of community, it's quite normal. And so if you study zero-point energy in detail, the best source of information is this community, because they are having all this made up, ready, so you can start calculating. And all that information that is usually taken for zero-point energy starts with these accelerator physics and exactly this picture. And so I try to emphasize it's not something on the side. It's very, very fundamental. And it's been used every day then. Okay, so here, for example, in these pictures, you see here is the start and here is the end of this particle. So here you have a boson, the photon in this case. So if they figure out these figures, You apply magnetic fields, that's why you have curves, and so from the curves you can then calculate how much mass and how much velocity you have. So this is basic for them, and they need the zero-point energy, otherwise they don't get anywhere. So now we are coming more to the applied field, so then we use the Casimir effect, which has been mentioned here a lot of times, and this is a basic picture about it. Well, the importance of the Casimir effect is that for the first time, we're not looking at single atom, single particle effects, we are looking at macroscopic effects. So Casimir said here the red plates are perfectly conducting metal plates, and these blue and these waves kind of symbolize the virtual particles, the zero-point energy. So what happens is that inside, between the plates, you have less states, less possible frequencies. So the sum of the energy density is less, and it's more outside. So you have a pressure indicated by these blue arrows. You have a pressure on these plates, more from the outside, less from the inside. This is a formula which you can derive after many pages of difficult quantum field theory. You can arrive at this simple formula, which doesn't even have electric charge or fine structure constant, but just speed of light and the dimensions involved here. So here, the virtual photons here, the metals here. So like I said, the importance is we come from stochastic, from random photons of the virtual particles of the zero-point energy. All of a sudden, we end up with a macroscopic measurable force. And that led also Puthoff in his papers. From this, you can easily argue that if this is possible to convert these random processes into something macroscopic, then you can also extract it as energy. Because, of course, this force can do work on these metal plates, and then you have extracted energy. So in principle, right here, you see that the energy density of the vacuum can be used. So here is another picture of the same thing, but it makes it more clear that you can have between these plates, you can have these sort of frequencies, they fit inside. This is electric engineering, and these longer waves, they don't fit inside. So that's why they are missing. So if you do your calculations then you have to leave out this low branch of these frequencies. And that's why you get this force on these metal plates. Okay, so this work already has been mentioned here before, and if you like to read about it, I recommend the feasibility study of Tom Vallone, which is quite a nice write-up. It's not that easy to get good scientific literature about the zero-point energy, because it's either for theoretical physicists very much narrowed down to certain aspects and very, very difficult to read, or it is way too simple to do anything with it. So something in between is difficult to get, but there are very few books out there. So these very important papers have been mentioned, so I won't go into them more. What I have not heard about so much comes up now. So the modern Casimir era basically starts with Lamoureux, who in 1997 published a paper that he did in, not far from here actually, in Los Alamos. And he did it on the site of his normal work there, in the basement of the Los Alamos labs. And he demonstrated and published in Physical Review about his Casimir force experiments. And after that, he sparked off a new era of other people who in the last couple of years, let's say in the last 5 years, have come up with several other new experiments that we will look at in detail just now. And you see one picture here. So, sorry, Lamoureux started it. So Mohideen in Riverside, California, he did some very nice work that we will look at. And Iannuzzi, he did it in the Bell Labs. He had this sort of setup. This is kind of a micro device. This is a silicon scale, so to speak. And here you have a ball which is about 100 nanometers. No, it's 100 microns, so 0.1 millimeters, and it's coated usually with gold. And here you have a piezo element which kind of allows to change the distance by on the nanometer scale very exactly. So this is the setup that Mohideen used, and we will look at it a little bit because it has become like of a standard workhorse in this field. Very simple, and it's basically a changed atomic force microscopes who have become very popular to look at semiconductors. And basically, you see, the only thing which is different is that you have a ball here. In a normal atomic force microscope, you will have a tip which has only 1 or 2 atoms on the top. And then what you do is you scan your object under this needle, so to speak, and then you measure the force between the needle and your object on a micro, nano, pico, Newton level. By this means, here you have a real picture of it. So you have a machined, worked cantilever out of silicon crystal usually, and you deflect a laser and you take these photodiodes here. And with this system, it's been widely used now because normally what you can do now is on a nanometer scale, let's say 5 nanometers, you can look at any object with this. It can be biological, it can be semiconductor, what you want, and without applying the usual difficulties of electron microscopes, you might be familiar with, you usually have to have conducting surfaces. Here you don't need that. So, but what Mohideen did, he used this normal setup of atomic force microscopes, and he glued this ball to it instead of this usual needle. And then what happens is you can now measure the force between the sphere here and the plate here, and you can change your distance here to what he used is like 100 nanometers to 1 micron. That is a variable distance. And with this setup, then he measured the Casimir effect. Why he's using a sphere is basically technical. It's much easier to bring a sphere close to a plate than 2 plates together, because if you want to bring 2 plates together, it's much more difficult if they should have on a nanometer scale the same distance everywhere. Very difficult. Much easier if you have a sphere, you just bring it close. You don't have to worry about alignment or anything. That's why all the successful people have used this sort of setup. And here you read piezo. Well, basically what you do is you change the distance by this piezo. They also have become cheap. So you can, on a sub-nanometer scale, you can very exactly vary your distance here. So this is like the workhorse setup. His measurement here is like this. So this is kind of the Casimir force reads here. So in piconewton here. And this is the distance. So you have 100 nanometers here, and you have nearly 1 micron here. And this aligns very well with the serial line. It's basically what you've read before, this 1 divided by distance to the 4th power, which is very typical for Casimir forces. We will look a little bit more now on the details of things, because Lamoureux was still happy with the normal Casimir effect calculations, but these measurements have become so good now that you need to advance the theory to real objects. Before we had ideally conducting metal plates, which don't exist, you know. So we will look a little bit more on the things which are in reality. So first of all, you have roughness, so you need a roughness correction. Well, here we have a measurement, and we see that the usual roughness of the surface used is about 50 nanometers or less. So if you only go to 100 nanometer, then you can still hope that the roughness is not too bad. And if you go to 1 micron in distance, then really you don't have much problem with the roughness. Temperature, it's always 0 point energy, but all these effects have never been measured at 0 energy. They're always measured at room temperature. So that's 300 Kelvin. It's a lot more thermal energy. So of course you have to take that into account. Then the Phenite Reflectivity, which basically is very important because what you usually use is metal, which is quite a good broadband mirror. But if you only around the plasma frequency. So usually what happens is for normal metals, it's around some sub-microns, something like this, maybe 100 nanometers in wavelengths, and below that, so it's like ultraviolet, and after that, usually metals become transparent, you know. So if you have a X-ray or gamma rays, very high-powered rays, which are still far below what we have discussed before with this 10 to the power 30 or so, kind of close to the Planck length frequencies, or that is definitely very transparent. You have to picture it like if you picture it in the atomic region, then these photons, they don't see much, you know. They have electrons somewhere there and the nuclei somewhere there, and all the rest is kind of empty. So they don't feel that mass much. So here we have a graph that I'd like to discuss with you, which kind of shows the situation. So, and the beautiful thing is that here, just around 1 micron, the Casimir force, this is like the correction to the Casimir force, it's a factor. So around this region, we have a factor 1. And all the experiments have been done in this region. So let's say from around here, so Lamoureux was from 0.6 to about 5, 6. So here you see that the correction for plasma, which means the real metal correction, and for temperature is not that large, luckily. So you can kind of get good alignment with theory and experiment. If you go away into larger distances, then the temperature effect will become quite prominent. And if you go to lower than 0.1 micron, then you have to very much take into account that the metals are transparent for that. So basically, if you go too close, it won't make any difference anymore. The plates are, if you picture it, if you bring it that close, that the distance between the atoms and the distance between the plate is the same anyway, you can easily imagine that it won't make any much more difference. Which is a little bit unfortunate, because if we really want to use these things as energy devices, we should go really much below this 1 micron, because we're still here on let's say, micro-Newton levels. So if we want to have kilowatt machines, then we have to go into regions of femtometer or something like this. That would give energies in the realm of the atomic, of the nuclei physics, you know, and then we would definitely have very good machines. It's just a question of how to do that. So, okay, here you have a similar graph for aluminum. And so the current research is as such. I have just found out maybe a month ago this about this nano case, which is kind of for me a very important landmark event, because the European Union is sponsoring a kind of a 3-country project. So I'm sure there are a couple of 10 million euros rolling there. So you have these people here basically which are involved in that. I haven't found out all the names and all the details yet, but it's definitely a big thing. You will see some of the pictures, what they are doing. So if you have lots of money, of course, you can make nicer experiments, and if you have to do it in your garage. So here's a guy that you should know, but I haven't heard his name here much, but he's actually inside this NASA new propulsion stuff. So we will look a little bit at what he's doing, and these are some more names. So here you see what this nano case is all about. It's nanoscale machines exploiting the Casimir force, So what all these people are aiming at is to enlarge the Casimir force to such an extent that it will move objects and more. So another reason why this is done, and also if you look at the people who are involved, quite a few coming from the gravitational physics, I think yesterday it was said that there is such thing as dark matter, and Tom made some comments like they call it dark matter to obscure things, but that's only very much half the story. It's basically like this. The community of gravitational physicists, they have their formulas, and it's all about expansion of the universe and stuff, and these Einstein formulas. And Einstein, he had the feeling that the universe should be stable, so he invented something called the Cosmological Constant. So he could change his formulas in such a way that it would be stable. He just had the feeling it must be stable. So on that basis, this cosmological constant was created, and if you calculate that today, well, there's not more reason for it than a feeling of Einstein. If you calculate that, you come to, in this set of formulas, to quite low energy densities of the vacuum, but you need some distribution of mass and energy in the universe to explain with the normal formulas the way things are going. This is one avenue. There are 2, 3 others, like the distribution of heavy elements in the universe. And so in the community of the gravitational physicists, they have, in different avenues, come up with this dark matter. And only recently, like a couple of years ago, they found out that there is such thing as zero-point energy, because they are gravitational physicists. They don't know anything about quantum mechanics, because the Einstein formulas and quantum mechanics are totally apart. There's not much to bridge it. Big people have tried it, but there's absolutely no progress. So the world of Einstein's theories, gravitational and relativity theory, and the other hand, the quantum mechanics, there's only very few connections like the relativity and quantum mechanics. So this is considered to be a hot topic in physics at the moment, that you have a very low energy density in the dark matter, and you have a very high energy density in the accelerator physics. So they're trying to bring that together, and because it's a kind of trying to get these 2 totally different viewpoints of exactly the same thing together. So that's why they somehow got the European institutions to spend a lot of money to find that out. But I think since they want to enhance the Casimir force, it's good for us that it happens. So I'm quite happy about it. Huh? Well, it's dark matter and dark energy. It's both. You have the only distinction between dark matter and dark energy is that dark matter, they allow that it also distributes and can accumulate at certain points, while the dark energy is not. It is very, it's everywhere the same. So they have these 2 things, and they have to bring that, well, they need both. And they come to about 70% dark energy and 20. They calculate it to the like 1 digit after, like 23 point, I think it's 32 point something, or 23.4% dark energy to dark matter. Well, could you push the escape button? Okay, here's some more detail on this nano case, if you like to make some search. So those who are really interested, for them it probably will be interesting. I'm also still trying to kind of probe into who's really inside all this. But it's definitely a very big thing, and if the European Union is sponsoring something, there are many millions involved, and I already know of 4 big universities involved, so it's quite interesting to see who is all involved and what they're doing. So unfortunately, the colors don't come out that nicely, but here we see a couple of pictures of the Birmingham group, which is also involved in this venture. And here you see their setup. It's all made to go one into these cryostats. So they really want to see what the zero-point energy is like on zero temperature and on other temperatures. And here's a setup. It's a interferometer with a piezo and all this. Here we have like a larger view of this thing, and so they really go for a precision measurement. Basically, it's a group which comes from the gravitational physics, so they really want to ask some questions to bring these two things together. How far they will come, I don't know, but definitely they are setting up a very nice precision measurement that we will hear about in the future, which takes a lot of, or brings a lot of pressure on the theory, because right now the theory is only like 1%. They can calculate to about 1% accuracy the Carcinoma effect because of roughness and of several questions, like, for example, are the virtual photons exactly as normal photons or not? All these are questions which are heavily debated. They bring questions like what formulas can be used. You know, if you look at textbook physics, it all looks very easy, but if you know more details, then you know that a lot of formulas only apply to certain situations. Like, for example, most of you think that electric field does exist, but for advanced physicists, the electric field, of course, does not exist. You know, there are only photons, which kind of then you perceive as an electric field. So the electric field is a concept that has been used in the 19th century, but in modern physics, you basically cannot use it, because the question should be asked, what is this field? What does it consist of, you know? And how does it propagate in time and space? So the very modern thing with the zero-point energy is kind of replacing the old electrical field concept. But on the other hand, to make some macroscopic calculations, it's quite handy to use the electric field. And if you do that, then you can use bulk physics formulas, and all these things are very heavily debated. Actually, there's a conference in September coming up where the debate will be very obvious again in Barcelona. I will show that in a couple of slides.
Do these cryogenic devices work with Bose-Einstein condensates at all? It seems like that might be to investigate zero-point energy on a different scale.
Well, the question with that's a whole different topic, you know, about the Bose-Einstein condensates. It's a good question, and things are happening there too. But this will be without Einstein condensates. So here's some of the references that this group is kind of pointing out. Here we see the old Casimir again, 1948, and here's one of the only books around which kind of really covers the subject from Miloni. And these are Bordak, Mohideen, and so forth. You see all the names that have been mentioned. And here is Astrid Lamprecht, and she's also one of the ones who are really involved in this nanocase project. Also a young professor at the University of Paris. So here's something from Jordan McClay. So check this out. He's involved in this NASA breakthrough propulsion project, and he's the one who demonstrated that there is a repulsive Casimir force as well. We will look at that in the next slide. And so this is the reference to that. He also made a Gedanken spacecraft, so he was making up a spacecraft out of zero-point energy. Well, and basically comes to the conclusion that at this point in time, if you only can go to a couple of nanometer or 1 nanometer distance between the atoms, and that's kind of your Casimir, the lowest Casimir distance that you have, it will be very difficult to build any device. But if you can somehow overcome that, then definitely it would be a great thing to use the zero-point energy. So here he's based in Wisconsin, basically, and so here you have the setup. Again, it's kind of a sphere, but here now you're not using a flat surface, but you're using these cavities. And then what happens if you calculate that? Then he demonstrates that you can have a repulsive force. So instead of the two kind of being drawn together, the opposite happens. And okay, we will look at those pictures in a second. I have to go back soon. So, so here you see that his results, his measurements, and here you see that in this region you have, with this kind of cavities, you have a repulsive Casimir force, while these are the flat surface results. So can we go back 2 slides?
Try backing up.
Okay, good, thank you. So here you see again, you have this, I would call it normal setup, kind of the cantilever, the ball, and your, basically all this is borrowed from the atomic force microscope. So, but you don't have to go out and buy an atomic force microscope, of course, which is calibrated and waste all this money. You just have to buy this cantilever and the LED and the photodiode. So you end up with a whole, with a couple $1,000, you can do these experiments now. So here you have the sphere, and you have your cavity here. So then you measure the force between the ball here and the surface with the cavities here. And you see a small deflection of the laser on these photodiodes. But luckily, all this is standard, so you can take a system that has been calibrated and used, and you can calibrate it to such an extent that you can measure pico and nano Newton forces. So here you see his setup. Picture doesn't come out that good, but the whole thing is hanging, so to kind of decouple from the normal vibrations. And then here inside you have your small nanometer setup, basically your little atomic force microscopes. Atomic force microscopes look just the same. So basically all you do is you change the needle into the ball and then kind of use the usual concepts that are used to make these things work. We've seen that already. Here you see the micronewton scale. Well, yeah, I like to point out, maybe for those who are very interested in the field, I really recommend this conference. It's, or just check it out in the internet. Go for QFAX 05 in Barcelona, and you will see who's coming and what they are talking about. And it will be all on the latest Casimir experiments and on all these things that I've talked about. And it's quite interesting to see how they debate there, and because there's a lot of open questions, you know, like even because it's called quantum field theory under the influence of external conditions. So basically, if you apply a field, or if mass is there, like a dielectric cylinder or a ball, how does it change the quantum field theory? How does it change our zero-point energy? That is heavily debated, and luckily now new experiments have come up where you can look at details of temperature, roughness, all these things that we didn't have before. So now new details are coming out, especially the temperature, for example, gives out different results than were expected, you know. So we can really expect new knowledge coming up from these experiments. Okay, before I go into this thing, I like to emphasize that with these new Casimir experiments, and especially, for example, with this nano case that really wants to enhance this force, I think we can expect also good news for our field, so that in the future, like at least nano machines will run with a Casimir force. You know, that's the next thing I hope for. Okay, now comes a small break. We will look at a machine that I have brought. Here you see it. I hold it up. It's a very simple device. Okay, there's no power cord attached to it. It's just, it has been sold, not in this form, but in the forms you've seen there or other forms, 36,000 times in Europe, especially Austria and Germany, with a guarantee that it works, and they sell between 5,000 and 10,000 US. So people are willing to pay for that, and I'll tell you in a minute why. So I think we have to get ready to start this animation. So basically the situation is you have houses, like in Europe, most of the houses are brick houses. Like only a small fraction of people live in wooden houses, you know. So, and usually they have basements. So here you have the Hungarian Parliament, and here you have this church and this house, which are very typical standard sort of houses. And here you have these aquapole. So now we start a small animation which shows us what is happening here. So click on that. Just click on that thing.
Okay, hold on.
Or start it directly here. Well, something happened here. Just start it directly, if you can. It's the same thing.
Already did. It's coming up.
Oh, okay. In just a second. Here it comes. Okay. We have to wait a little bit till you know who made this animation. So.
Building picture. Where was that building?
That's a Hungarian Parliament. So it's in Hungary. So here's the situation. Okay, water somehow comes into the soil. Note that on this side of the building you have a protection, usually like tar, and but the rest of the building is not that well protected. So the water comes in, it puts kind of a pressure on the walls, usually bricks, and then what happens is that the walls get wet. This is a very common phenomena, that a problem that many people face, that their basement is wet and even the wetness goes up high into the house. So since I think most of you don't have a brick house, you probably don't know this problem, but those who do have them, they know it. I've just been on the East Coast and I mentioned that this exists, and immediately a couple of people said, where can we get it, you know, because they had the same problem. So here you see that it's a capillary problem. Okay, the bricks, they have very small pipes called capillaries, and they suck up the water, which is kind of a very simple effect. I hope you've heard about that one. And so then what happens here is that slowly the walls degenerate, and the protection, which is usually like, I don't know what it's called here, but you have the bricks and then you have the, what is it called? Then you put like some more cement on the bricks, and but that kind of falls off. We missed that part, unfortunately. But here you have now the effect of this thing. All you do is you hang it under the wall, and the water goes down. So that is the thing. So here we see that it pushes down the water in the capillaries. So, and then here you see how it works. There's nothing attached to it, so somehow it converts fields, and he says the Earth field and the zero-point energy, it converts it. There are basically some spirals inside. So, don't ask me to explain this, but I guess we can't go back. Or can you run it again?
Pardon?
Can you start it again?
Yes, I can.
Then I just want to point out a few more things. I want to explain how it's usually done. You see, usually people who really have a problem with this water, like it was shown here, they are spending like 20,000 US to get it done. You know, what they have to do is they get a team of people, and they cut with a big saw, they cut at the bottom of the wall, they cut the wall, and they push in steel plates. Okay, just imagine that, a lot of work. All the walls of the house in the basement are cut, and steel plates are pushed in, so the water cannot come up through the capillaries anymore. And then you put in big heating systems and ventilation into the basement, and with a lot of energy, you bring out the water. So the whole process creates a lot of dirt, it's expensive, and it uses up a lot of energy. So the alternative method to drying your wet walls is to just hang or let people hang these aquapole units in the basement. And compared to what the normal costs are, they are definitely considerably cheaper. They cost maybe half of it or 1/3 of. So usually here the walls are cut and steel plates are pushed in, okay? Then you also have to do what is done here. You have to protect the wall, so you have to dig up this and put the tar, and then you dry the whole thing, okay, with a lot of heating. That's the usual way how it's done. Okay, can we go to the next slide now?
You say it again?
Next slide.
Okay.
So, yeah, that's not the next slide. We'll go back a couple. You see, no? Okay. Now forward.
Hold on.
Okay.
Okay, go ahead.
No. One more escape. There's a, yeah. Okay, so this is a Hungarian Parliament, and they did only part of it, but it's still huge compared to what they usually do. And within 1 year, they dried the thing. Of course, naturally, you have the water here. You can imagine that this building out of sandstone will have a massive water problem. So here, well, that was good. Anyhow, you would just see that this cement on the walls falls off. Okay, here's some pictures of how it works. This is a capillary effect, sucking up water into small cavities or small pipes. This is one description of the inside of this. This unit here is made a little bit different, but so basically you see here different coils, and it's totally passive. There is no power cord attached to it, and the effect of this is quite large. I know, like if a government agent asks me, do you know any free energy device that is really working, then I say, yes, I do. And because this thing has been sold 36,000 times, and he gives a guarantee. So if your basement does not dry with the system, he gives you your money back, you know. So still you find lots of people all over, churches, government buildings, who have used this system and are quite happy with it, you know. And he got a very noble prize in Austria, one of the largest awards that were there for the people. He got one of those. So he's quite a made man in Austria, and they really like his system. Despite that no scientific person will really be able to explain how it works, you know. So I think it's quite an interesting device. And let's see here. Here are some more problems, you know. So I call it wet wall scenarios. So only which is quite typical, the capillary wetness that comes up through these capillaries, that is the one that this system will work on. All the other scenarios, many other scenarios of how water comes into the walls, it will not work on these things. So, so I know some people, they always like to have machines that bring power out immediately, but well, this has been widely used, and I think it's good to have something that, you know, works reliable, spreads, and it's also good for us. So, okay, if there is rain coming here at the walls, or here you see like a sink which has a broken pipe to it, all these scenarios, of course, have to be looked at into a different way. You have to get rid of those by other means, but of course there are other conventional methods to protect your house.
What's the button?
It's not shown. So just after this, I think we can start this #1 film and just look into it a little bit. I like to mention that the price for the unit is, well, let's say a little bit overpriced, but you get a value that you would usually have to pay more. That's why it sells good. And he has service and guarantee. So Service means there are two people coming there, like a team. They drill in small holes into your wall, take out some stuff, measure how much wetness is inside very accurately before and after, and they monitor the development of your house. They look at the house very carefully also to spot other reasons for the water. And so that's the service. And they, with precision instruments, really measure how much water is in your walls, so that at the end, when you see, okay, it doesn't work, you get your money back, or they can really demonstrate, yes, it has become better. So since it's not been marketed in the US, if anyone is interested to get into this sort of thing, I'm not sure if that's a good idea here in Utah. I don't think they have much brick houses, but in the East Coast, I'm sure if you market it right, it will probably be a seller. So can we start that film? We just browse into the film a little bit, so you see some houses, you will see some of the effect that the water does, and you will also see the team. Well, there's some problem here. Well, the format, of course, is a European format, but but it's just a file. I don't think it should make this difference.
It didn't do that a moment ago.
Yeah. It doesn't do it on the screen. It just does it on the...
It does it up there. Yeah, I don't understand that. That's... We need to speed read. Yeah, you need to read very fast.
Well, I'm not sure if we can watch this film here because there seems to be some problem. But maybe we should take some questions instead. Okay, Tom.
Thorsten, your protocol is actually explained by Dr. Stephen Hallwinger's life wave device.
Oh, really?
Privileged, yeah, I was privileged to be in the shuttle today with him this morning, and I got the inside scoop. In fact, he's here to tell you how your optical works. And because his device works on the same principle, it's a passive amplifier of certain frequencies. And you saw the pyramidal shape of the water molecule, which I'm trying to show you, and I don't know how hard you can get, is the primary frequencies that activate the water molecule.
Uh-huh.
So the coils that are inside the passive device are basically causing the water molecule, they're repelling the water molecule by amplifying the correct frequencies. And maybe Dr. Hallwinger can explain a little bit.
Well,
better.
maybe you can give me some reference on that. I'm sure the guy who produces it, he will be very happy to have some more backup.
You want to give it a try?
Because it's always good if you have something, you can also explain by theory how it works, because otherwise people always think, what is this guy doing, unfortunately. Even though he has the luck to be in Austria, where by some reason it's a smaller community, I don't want to say we look down on them, but it's in Germany things are more tough than in well, yeah, I'd rather have the reference instead of hearing the whole explanation now. But you can
I'll give it a shot. I don't know if it explains this, but I can explain what we did with the LifeWave patches, which David Schmidt, the inventor, created. I am the science director. Is that we use a solution-based self-assembly nanotechnology process. So we take a solution of optically active molecules. We put them in a proprietary processing, and they will cause a crystallization of geometric forms in the patch. Now we have a material that has electrically conductive properties. They're liquid crystal semiconductors. The organic liquid crystal semiconductors, when they're placed in the patch, they have a geometry to the crystals. They are placed on the body, and we use the body's own magnetic or electromagnetic field in the infrared range to activate a signal that's resonantly sent back into the body. Now, that's using to activate enzymes in the mitochondria to turn on fat metabolism.
It reminds me of, there's some more interesting thing about this machine. They are now doing a field study with a university or trying to reverse the effect to bring up water where they're like in a desert and stuff, so it's quite interesting development. Well, I think there are more questions here.
Is it possible to amplify existing background radiation? It could be ELF, it could be Earth-based, could be
Could we refrain from asking questions unless you have the microphone? Because for the benefit of everybody else here, they can't hear you, and it's not on the tape.
Okay, I've got the microphone.
It will come down to you, okay?
I'm curious for you to research something when you get back to Germany. Find out how many dead rats are in the basement. Because if you're taking water out of the bricks, out of capillaries, this would also probably work good for getting rid of termites.
Good question. So there's some use in wooden houses as well, you suggest? Ah.
Oh, thanks. Yeah, my question, I guess, essentially was from more of an electrical engineering perspective. This thing wouldn't necessarily, I mean, it could be using zero-point energy, but what I'm wondering is, could it also be using, and I guess this would be related to something Stephen Greer showcased potentially a few years ago, some kind of background radiation from FM transmitters, you know, ambient energy, right? Cell phones, ELF from the Earth, background noise, in essence. The reason I ask is there was a device that was unveiled by Stephen Greer's team, and the claim was that it was able to light light bulbs. They would place it on a sidewalk, not near anything, you know, that wasn't near electrical means, so it wasn't inductive. But at the same time, supposedly they were able to light several hundred watts worth of electricity. Now, they never got a good look inside of it, but as I understand it, did have coils. So,
But if I may answer, no, I don't think so. The reason is, they're just basically a few coils inside, you know. So it works somehow with tuning, you know. So I'm quite sure it's a different phenomena that hasn't been. It's not that easy to explain it. It's not using a radio station and kind of changing it and so forth. I don't think so. It's more like what has been said before and what Tom said also. It kind of really gets into this water molecule and uses some interesting effect in this field to. It reverses the voltage also because you get a voltage on this wall. You can measure that, and it reverses this voltage. You know, because that's been used also to get down the water. You put electricity. You know, because there's a voltage, and if you forcefully reverse that, water also goes down. So there's like a complex chemical and electrical effect in the play there. Yeah. Okay, wait for the microphone.
Okay, what is the, my question would be, what is the rate at which the water moves through the wall? And also, if you're getting a potential, what is the potential? And also, do you see any type of electrolysis?
Oh, well, about the electrolysis, I don't know. The speed is, well, usually is, you get, well, a year or 2 years. That's about when it's drying, you know. Like this speed you have to allow. And the reverse of the voltage, I heard, is much faster. Like after a few hours, it starts to reverse, and it's a couple of volts. That is how much voltage it has. So we're starting the movie. Let's see what happens. We continue with the questions, and if something interesting comes up, then we.
Just continue the PowerPoint?
The PowerPoint, I think, is over. You can't start the first movie. Because I haven't looked at the first one and the second one, I'm not sure if that's...
It looks good on the screen here, but it comes up, scrambled up there.
The first one.
Yeah, let me try the first one again.
Okay, he's fiddling with a movie, then you see a little bit more about it, yeah?
Yeah, first of all, do you have to use a Casimir cavity to extract energy from the Casimir force? Do you have to have that actual cavity present in order to do that?
Well, you see, Casimir, the interesting thing about Casimir, he just laid out a very simple scenario, 2 ideally conducting metal plates. Of course, you can have all sorts of other similar setups using totally different scenarios that will do the same thing. All you need to do is, and what he's doing is, he's restricting the amount of possibilities in the vacuum, okay? So less possible states.
Ludwig,
and that creates this force. So if you do that by any other means, you know, instead of using metals, other geometries, other fields, whatever, you will get similar effects, you know.
I have a few comments too. First of all, aluminum goes transparent at 5 nanometers, and I'm wondering if it's possible to have several orders of magnitude stronger Casimir forces.
Just jump in here, and then you can continue.
Oh, okay.
Because this is an important part. Here you see like what happens when the walls get wet. Okay, this is a very typical kind of indication. The paint goes off, the shielding of the wall, whatever you call it, falls off, things like this. Okay, continue.
Yeah, I wonder if you can have several magnitudes of increased Casimir force if you try to bring 2 protons together.
With up to protons, yeah.
And also, Robert Forward mentioned that you can use atomic spray guns to lay atoms evenly to have a perfect Casimir plate also.
Yeah, both is yes. I mean, if you have a very nice surface, it will be better. And aluminum might be a good choice. I'm quite sure they have not used aluminum. They have used aluminum sometimes, but gold is kind of more popular because it's cheaper, and it's cheaper to have it in a very pure way. You know, gold is one of the cheapest metals you can buy if you want to buy them pure. Okay, here you still see the same thing there. Was there any other part of your question? Scenarios like bringing 2 protons together. Okay, it's but then you don't have this macroscopic effect. You know, you won't have real objects moving, doing something, so you can come to machines and stuff. You know, if you have just atoms flying around or accelerators and stuff like that, that doesn't bring you real energy machines. Okay, maybe we watch a little bit of the movie and then we go back to the question. So here you still have the same animation. You've seen now the real objects. Maybe we can jump a little bit.
Okay.
Jump to 13, for example.
Okay.
That's like way here somewhere.
Okay, there's 13. There's 13 right there.
So the last thing I want to show on the screen is how they actually people who go there and they measure. See, here are some people they are setting it up. So they are putting them on stands. And so this is inside a church. Setting them up, aligning them. I hope that other part comes soon. Yeah, okay, here you see they measure the voltage. Can you read it?
Yes. Say it again.
Did you? Okay, here you see that's how they kind of determine how much wetness is inside the wall. You drill, and then you take that and there are several professional methods to really get the last bit of water out. So they're explaining that here, how it works. So you have like some chemical which is inside a glass, and if you shake it, then the chemical comes out, and there's a chemical reaction. And by the pressure which then comes out, you definitely know how much water is inside. These are just standard methods that they use. Okay, I think we let it run in the background and you watch it and we make a little bit of light and finish the questions.
Okay, should we shut this off?
No, let it run.
Okay.
So there's a scale and then you weight it before and after, and then you also can determine how much water is inside. Okay.
You have about 5 minutes.
Okay, so any more questions on this and on the 0-point energy? Huh? So is there anyone who wants to ask a question? There's one question there, one question here.
Testing? Okay, we're On that water device, is there a complete schematic available?
No, not yet. I mean, you can somehow communicate with these guys, go to their website, Aquapol something, and go by Google and then try to order it from Austria. But, yeah.
Has there been any test on possible health effects? I mean, you're draining capillaries of water.
I'm not sure if they have done any field studies on that. He claims people become better from it, naturally. So, but I'm sure he sticks far away from anything claiming health risk or benefits, because that's even more tricky than here. You know, you only have your FDA, but we have the whole government. You know.
In the 0-point field, Don Smith clearly has discovered something there. How does that fit into some of the research? Has there been any studies done on his, or will there be?
I'm not aware of that. But there's no reason why not.
Are there any more questions for Thorsten Ludwig?
But maybe
one
I can
more in the
point out,
center
because
back.
if devices come out, you see, just a few comments on the inventors and maybe some people who sit here in the audience, they always think, well, if some device is out, immediately, you know, some university institutes will jump on it and try to find out. That's not how the world works anymore. You know, the most people in science, they are paid for very exact projects, you know, like developing this, developing that, and they have absolutely no room to go left or right unless they do it on their own accord, privately, with their own resources, you know, then they can do it. But there are only few, some of them probably sit here in the audience, who do that, you know. But the main institutes and so forth, it's a very strict sort of organized thing, because the single scientist, he's very much under pressure. He has a contract, he needs to do what has been asked. And the levels up, there are always contracts and so forth. You know, there's hardly anyone in science who leisurely kind of does what he likes to do. You know, I mean, that's just a thing which doesn't enhance that anyone will look at a machine. You know, it's only if there's a lot of personal interest that will happen.
Is there any possibility that in Don Smith's machine that maybe fields are bringing out the Casimir effect?
Yeah.
Fields bring, oh, hello? Hello? Yeah, fields bringing out the Casimir effect possibly in Don Smith's machine.
Well, yeah, everything is possible. Like I said, very little is known about how the zero-point energy is affected by fields and objects and things like this, you know. So since it's not known, it can always be. You know? And
Okay. Okay, looks like that's the time we have. As I had said before, we really aren't going to do much with a lunch hour. We are going to